Hello guys, good afternoon. How are you doing? Good, excellent. So let me set up all this stuff here. 1 second, please. Have you been able to do the Kappa model? Have you tested the Kappa model? Guys, have you done that?
Yep.
Perfect. So what was your conclusion? The model holds or not? Let me share my screen. What do you think, guys? What was your finding? So remember this model, guys, the final equation is simply
using for your
Yep.
y and x variables to run the regression for the model.
Right. So let me go on there. This is completely right. So when we have, this is the Kappa model, do you agree, guys? Okay. And basically what the Kappa model is saying that the risk premium of asset I is proportional to the risk premium of the market. Okay, and this proportionality is given by beta, that is simply the covariance of between asset I, returns of asset I, and returns of the market divided by the variance of the market. Okay, so if you remember well, guys, this is exactly what we get from our OLS model. It's a covariance divided by the variance of the exogenous variable. Right? So the thing that you need to always talk when you try to test the Kappa model is, do we have alpha opportunities? Do you remember this one here? We did this in the security market line. Okay, so do we have alpha opportunities? According to the Kappa model, guys, it is a general equilibrium model. We should not have alpha opportunities, right? So this implies that alpha should be significantly or statistically equal to 0, right? So what I will do is I assume, I think in the data set I told you, assume that the risk-free is 0. Technically, now it's 0. Okay, so my model is going to be simply expected return of I equals, I will say this, beta expected return on the market. Make sense? So, and what I will do is I will add alpha here. Okay, remember this is my alpha intercept. So I'm completing my regression. So this is my regression. Okay. Do you agree?
Professor.
Yes.
Sorry to interrupt you.
Go ahead. No.
Suzanne is waiting for you to let her.
Oh, yes. Sorry.
Yeah.
Yes. Here we go. Yep. Okay. So this is my regression. Do you agree? So you know this is exactly the same. If I call this y equals alpha plus beta x, that's it. And so statistically, guys, what we need to do, remember, is a regression. So I have errors here, etc. So I have an error here. So it's observation. And so from here, what I can do is I can compute the estimated alpha, that is going to be A, the estimated beta, that is going to be B, correct? And that's all. And so we have all our techniques to do that. And the only thing that you need to remember, guys, is that Kappa works on returns. Okay. One way of defining returns, the easy way to define a return. So the return on period 1, for example, equals price in period 1 minus price in period 0 divided by price in period 0. Later, we're going to use the logs, but at this point, let's assume that the normal return. Right? If this is true, what you should have, and let's do this very quickly. No, this one here. This one here. So this is the data, correct? This is the data that I provided yesterday or last week. You have this data. Agree? Guys, you agree? The file was called CapM data or something like that. And I remember you told me that you have received that.
You mean the two data sets of the IBM and S&P 500?
Yes, exactly. Exactly that. Okay, so the first thing we need to do, guys, is simply compute the returns. Okay, and if you can see, what I've done is I have applied the formula that I just wrote. Are you looking at my Excel, right?
No.
No. Oh. Sorry. Why is that on screen? Now? Yes, perfect. So what I've done here, so this is the data IBM SP500. So IBM is my asset I, and SP500 is my asset market. I mean, it represents a market very well. And what I'm doing, first of all, is I'm trying to compute the returns for period one. It's going to be this number minus this number over this number, etc. And I do exactly the same. And I do exactly the same for SP500. Okay. So what we have is basically if we go down, we have 11,080 something observations. We have 11,081 observations. Make sense? Okay, and then from here, guys, we continue using Excel. This is going to be the last day we use Excel. By the way, have you installed eViews, guys? Have you been able to install your eViews? Good, yeah. Good. So we can start. Perfect. So now we go into serious games. Good. So if I run my OLS model, remember is you just go data. What is my data here? Here we go. Data analysis, and then you go into regression. Okay, you enter the data, you know, my Y input, my X input, my labels in the first row, my output range, etc. And then you simply run this one here. And what you get is this table, this result here. Okay, let's comment this very quickly. Now, how do you read the R square? Someone can read the R square. What is this 0.407 meaning? What is the meaning of that?
Professor, it means
yes.
the relationship of X, the way that X relates to Y, right?
What type of relationship? Linear or variance? Or volatility or variability?
Variability.
Because remember, R squared is R squared. It's a variable squared. Remember? So it's the way you need to read these guys, and please pay attention because the people confuses this one. If you tell me that simply represents 40% of Y is explained by X, you are talking about levels. Okay, that's incorrect. What you need to tell is 40% of the variability of Y is explained by the variability of X. Got it? So that's the way you interpret it. Good. So what is the difference between the adjusted R squared and the simple R squared?
The adjusted R square is preferred if the sample size is small.
Right. So you basically control for a sample size. In this case, why these two guys are exactly the same? R squared and adjusted R squared.
Because it's a very large sample.
Exactly. The sample size is 11,000. You see that? So the difference between these two is almost nothing. So remember the R squared adjusted is, you need to be very careful when you have the small samples. Okay, remember that. Okay, so what is the hypothesis of the F test? Or Anova test, also known. What is the null hypothesis?
That there's no linear relationship.
Exactly. There is no linear relationship. Got it? Now, of course, if you want to go to the tables, you can use the F critical value with how many degrees of freedom is going to be 1 divided by 1, 11,079. The F is going to have these degrees of freedom. Got it? And then you use this number here, and then you simply see if this number falls in the rejection zone or non-rejection zone, and then you decide accordingly, correct? However, you don't need to do that. You can use this significance F, guys, is your p-value. Okay, at the 5% significance level, guys, what can you tell me about the null hypothesis that there is no linear relationship? Come on, guys, tell me.
Since the p-value is less than 0.05, so we reject the null hypothesis.
Correct. So you are rejecting that there is no linear relationship, thus there is linear relationship. Correct? Do you understand that? Guys, you're going to learn a lot if you study. Otherwise, you're going to start getting, lost very quickly. So you need to study, guys. Study. Just 1 hour a week, I'm pretty sure that you can just review what we have done on the video. And 1 hour, that's more than enough. You're going to see that that's more than enough. Got it? Okay, so we have linearity that, 40% is okay. Decent. For finance, 40%, guys, in the R-square is very high. Right? We're going to see examples in which our R-square is going to be much lower. Okay, guys, so what can you tell me? Where can you see if the Kappa model works? Remember, my Kappa model, guys, is, where's mine? My Kappa model is this one here, right? Is this part here. And what I'm testing is this one here. So basically, in order for me to say that a Kappa model works, is to find that this one here is statistically non-significant, correct? So that's technically 0. Because if this number is 0, this part disappears, and then what do we get? Exactly the Kappa model. Do you agree? Okay, so now let's go to the Excel again. What do you think, guys? So this is 0.0007. Okay, if you see this number, it looks very small, right? But don't trust on that, guys. I've had very significantly large intercepts that they are statistically non-significant. Okay, so the correct way of seeing this one here is looking at your t-stat or your p-value, correct? So the t-stat, remember that the only problem with the t-stat is that you need to use the t-tables. Now, how many degrees of freedom has your t-table if you want to use the t-tables? Degrees of freedom, guys.
n-1.
No, in this case, yeah, you're right. n-1 is when we have only one restriction. In this case, how many restrictions we have? It's going to be, in general, guys, n-k. Okay, and k represents what? The number of coefficients that you're, or the number of variables that you're including in your model. So in this case, your t is going to be equal to n-2. So basically, what we're saying is 11,081 minus 2. So it's 11,079. It's a huge number, degrees of freedom. So how do you imagine this t is going to be compared with a normal distribution?
Almost the same.
Exactly. Okay, remember that t and the normal are different when the degrees of freedom are small. Just remember that, guys. Remember that. Okay, so what can you tell me using the p-value? So what is your null hypothesis, first of all? Okay, let me go back to my whiteboard. So what is your null hypothesis when you do null hypothesis for A? What is your null hypothesis?
Not significant.
Yes, and so this means that, sorry, alpha, no, because the hypothesis is based on alpha. I believe that alpha, so my population coefficient alpha equals 0 versus my population coefficient is not equal to 0. So this one here in statistical terms, econometric terms, guys, means non-significant or not significant. Correct? Okay, so now let's use our result and you tell me. What can you tell me about that? Do you reject nor reject the null hypothesis?
Do not reject.
Why?
The p-value is greater than the confidence.
There's no, not confidence, significance level. Remember that the significance level is the 1 minus the confidence level. So if we have a confidence level of 95%, 0.95, 1 minus 0.95 is 0.05. This is your significance level. Okay.
Yes.
Yes, so 0.57, of course, is much larger than 0.05. So we fail to reject the null hypothesis. What is my null hypothesis? Not significant. So this implies that we can be statistically correct on saying that this number here is 0. So basically, guys, with this number here, with this decision rule here, what we are saying is that really the CAPM works. Agree? So the CAPM, guys, means when you have an alpha opportunity equal to 0. So this implies basically you don't have alpha opportunities. Right? So you don't have arbitrage opportunities. Now, pay attention here, guys, because in finance or in economics also, not existing of arbitrage opportunities doesn't mean that arbitrage opportunities does not exist. Okay, so it kind of looks like a contradiction, but the idea is the following. If we find an arbitrage opportunity, you know, you're not going to be the only guy in the market looking and finding this arbitrage opportunity. So what is going to happen? Everyone's going to jump into the pool. What happens when everyone jumps into the pool? Simply, we go back to equilibrium. Got it? So what this model tells you is that, yeah, there can be some arbitrage opportunities, but in equilibrium, there are none. Right? And this is this alpha. This basically this alpha is telling you there is no extra by investing in IBM. Now, what do you see here, guys? Is beta significant or not? Is statistically significant or not?
Significant.
Yes, it is. Take a look to the p-value, guys. It's 0. So 0 is smaller than alpha, so you reject the null hypothesis. My null hypothesis was what? That beta, that in this case, Excel calls it x variable 1, the name of the first variable. That beta is different from 0. Make sense, guys? Okay. Now, remember, this 1.1, and we're going to do the test in EViews later. What is interesting about IBM, guys, or these big names that are already mature corporations, these names are always expected to have a beta around 1. Okay, so they basically move with the market, very, very close to the market. Okay, and we can see that. We later in EViews, we're going to do a wall test. And what we are going to test is, you know, even though I see that this number is equal to 1.1, can I argue statistically that this number is equal to 1? All right, so that's the hypothesis that we're going to do in the near future. Make sense to you guys? Okay, easy, clear, so you should be able to understand this part very easily now. Questions, comments?
I have a quick question about the
Yeah.
confidence level.
Mhm.
Is it just always assumed to be 95% unless we are told otherwise?
Yes.
Okay,
Yes.
thank you.
Yes, you know what? In here we don't have the option to change this. Okay, Excel is always going to give you a 5%. Right?
Okay, thank you.
EViews we can change, but no, sorry. You can do this in Excel also, of course. I'm talking nonsense stuff. Take a look. If you go to the regression, here is where you can put your confidence level. You can change this to 90, 99, whatever you want here. You see my Excel?
Yes, thank you.
Okay, perfect. Okay, guys, questions, so we can continue moving. No? Okay. Okay, let me move to the next screen. So what I will do this year, guys, is I will present all the variations of the model, and then I will go into the assumptions, and we're going to run very quickly. I will do. There is some mathematics around here. It can take me 5 minutes to do. What I will do, guys, is as I will simply present from here to here, I will jump, and then I will prepare for you a small video giving you the details of how do I arrive to this conclusion. Got it? Okay, just to move. Okay, so what we are going to do is what we have done is a univariate OLS model. Okay, the very simple model where we have alpha plus beta x plus my error. Agree? Why is it called univariate? Because I have only one regressor. Now let's move into something more useful. The multivariate OLS model. Okay, so here I need to be sure that you understand what we are going to be talking about now. So imagine, guys, that I have a series of y and x1, x2, x3, xk. So we have k variables, okay, that are going to be, we are going to analyze to determine the behavior of y. So imagine now that we just collect the first cell of Excel. You see, so the first row of Excel, that's what I'm going to write here. So this is going to be y observation 1. It's going to be equal to a constant. It's called alpha. It's going to be plus, and I have a variable 1, position 1. So when I talk about xij here, this is variable number. And this one here is observation number. Okay, so this is variable variable 1, position 1, observation 1. And I will have beta 2, variable 2, position 1. And then I can do beta k, variable k, position 1, plus my error 1. Okay, so this is the first row of Excel. Of course, in Excel, we don't have the error. We're going to compute the error later. Now, if I do the second variable, the second observation, no second variable. So it is y, second observation. It's going to be, again, a constant, beta 1, first variable, but second observation, correct? Guys, you agree? The second one is going to be beta 2, second variable, second observation, beta k, k variable, second observation, plus the second error. Okay, so if you do this several times, guys, assume that we have n observations. So y position n, the last row of Excel, is going to be equal to alpha beta 1 x observation, x variable 1 observation n, plus beta 2 variable 2 observation n, plus beta k variable k observation n, plus its error. Make sense? Do you understand what I'm doing? Okay, so now what I need to do, guys, is I need to use with matrix algebra. I need to create these matrices, write this in a matrix form, right? And you follow me. So what I will do, all of you have taken linear algebra? Have you worked with matrices before? No? Okay, don't worry. What I will use here is that's why I've done this one here. So do you understand this part here? Okay, perfect. So now, if I want to write this in matrix form, guys, so what I will do is I will simply collect all the y's in a vector. Okay, and this one here, so this is a property of multiplication. I will explain you in a minute. What I will collect here are only the x's. So this is going to be 1, x1, 1, x2, 1, xk1. You see, I'm just collecting the k's, the x's here. Down is going to be 1, x1, 2, x2, 2, xk2. Then if I continue doing this stuff, this is going to be 1, x1n, x2n, xkn. Okay, and then, guys, what I will do is I will multiply this by alpha, beta 1. Can I do a change of variable for a minute? No, that's okay. And no, better I do a change of variable. It's going to be much simpler for you. Can we do, give me 1 second, guys. Instead of alpha, I will use something different. I will use this one here. It's going to be called beta 0. Okay, just to make it easier. Okay, so beta k plus my errors, E1, E2, En. Now, guys, what is interesting is you remember when you have a matrix multiplication, you need to do this row times this one. So first of all, this is an n times 1, correct? So we have n rows, 1 column. This one here is going to be an n times k. So we have n rows, k columns. And this one here is going to be a k times 1. This one here is a k times 1. And this one here is an n times 1. So you can see, guys, that the rule of multiplication, James, don't worry about this. We just need to mention this. The rule of multiplication in matrix algebra or matrices is that the number of columns of the first one should be equal to the number of rows of the next one. And the resulting matrix is going to be the n from here and the 1 from here. It's going to result in n plus 1, n times 1. Now, the rule of sum tells you that you can sum if and only if the matrices are conformal. So basically, if this is n times 1, this must be n times 1. So you can sum these two, and indeed you obtain an n times 1. Got it? So if we simplify this, guys, what I will call this matrix here, perhaps I can do this here. I will call this one here y. I will call all these matrix here x, all these matrix here beta, and all these vector here errors. So this is, guys, this is the notation of the multivariate model. Remember, y is an n times 1, x is an n times k, beta is a k times 1, and epsilon is an n times 1. Okay, so these are matrices. They are not individual observations or individual variables. So x can have k components. Okay, so that's the multivariate version of the OLS model. Okay, 1 minute to copy, and we can move. Ready, guys? Make sense? Okay. So now, guys, remember what we try to do in the OLS model is minimize, remember, the sum of squares of errors. Remember that? That was our goal in the univariate model. Okay? In the multivariate model, the version of this is going to be simply minimize. This is the sum of square of the errors. E prime E is exactly the same, guys, in matrix notation to this number here. Okay? So for example, so this one is going to be a 1 times n. This is going to be an n times 1. And so the result is going to be a 1 times 1, correct? It's a number. Okay, but the number is going to be a square. Take a look, guys. So imagine that E, Okay, I just will do 1, 2, and 6, for example. This is my E. So this E is 3 rows times 1 column. Now what I will do is, what is E prime times E? E prime, simply transform this one into a 1 times 3 is 1, 2, 6. This is E prime, E transpose. And then you multiply this by normal E. And then what do you obtain? The multiplication is this times this, 1 squared, this times this, plus 2 squared, this plus 6 squared. Do you agree? So what is this? Exactly the sum of errors squared. Okay. So the condition now is going to be minimize E prime E. And if you do this, guys, I will provide you the math proof later, okay? You're going to find by simple algebra. I will explain this to you in another file. Indeed, it's very simple. It's much simpler than the univariate model. Oh yeah, B is going to be equal to x prime x to the minus 1, x prime y. So this is the model, guys, that we're going to be using. Okay.
Professor, can you go a little deeper into the economic intuition behind mathematics?
Between the economic intuition of this error square, how to arrive to this part?
Yeah.
Yes.
Sure.
So remember, it is exactly the same intuition as the univariate model. So that's why I dedicate a lot of time on this model here. So, okay, let's assume again that I only have x and y, right? And then I have a cloud of points. You agree? So this is a scatter diagram. So this represents, for example, this point here represents x1 or xi, observation I, that is matched with observation I. Do you agree? What we try to do is we try to find a line that best fits all the data, correct? So this is my y fit. How do we call this part here? We call it error, correct? So what we try to do, the line, the criteria to find the line is going to be try to minimize the sum of errors squared. Agree? So what we try to do is try to move the line. Okay, perhaps this line is not good. Perhaps we move down in order to satisfy this condition. I want to find what is the position of the line, okay, based on alpha and beta, where my alpha and beta are going to be located in such a way that I minimize the sum of the square of these errors. So the errors are going to be, this is an error, this is an error, this is an error, this is an error, this is an error. All of them are errors, do you see? Okay, so the economic intuition is more statistical or mathematical intuition. It's simply, I try to find a line that is basically approaching, that is satisfying the condition of minimizing the sum of the squares. Now, the economic intuition, guys, at this point, we're not talking about causality, okay? So it is different. So what we're trying to tell here, okay, informally, what we try to say is how the variability of x influences the variability of y, got it? Perhaps if we have some economic theory or some theory on our back, we can argue that x causes y, got it? But not necessarily true, okay? And there is a lot of discussion as we're going to be discussing in a future class, guys, about endogeneity problems. But indeed, what we believe is that x has some influence on the behavior of y. So x causes y. Again, I repeat, we need to be very careful with this term at this point, but that's what we're going to try to do. Make sense?
Got it. Thank you.
Perfect. Okay, so now we can go into yeah, I think we can do some Excel now. You have I will show you guys, and you need to replicate that for the first midterm. For the second, from the exam that is the quiz that is coming, I don't know, in 2 weeks perhaps. So you have this data. Okay, and basically this is a profitability, yearly profitability of McDonald's. Okay, these are real data in, I think it was millions or hundreds of millions, I don't remember. Okay, but the profitability of McDonald's depends on two cells, the counter cells and the drive-up cells. Right? So obviously here the relationship is causality, do you agree? So the sales on the counter and the sales on the drive-up definitely cause profitability. Profitability is not causing the other two guys. Makes sense? Well, we can argue that can be, but here I believe that it is a strong causality relationship. Correct? Okay, so the only thing that you see here, guys, is that instead of having one X, I have two X's. So this is already called a multivariate OLS model. How do we run this in Excel? Well, very simple. You do again the same process. Data, data analysis, regression, and then you select my Y input is going to be this one here. My X input is going to be these two guys here. Okay, I have labels, so the names are on top of this. I want to keep the 95, and I want simply to select where I put my results. I will put this in E. Right? So if you run the regression, guys, you obtain these results. Look very similar, do you agree? That's the beauty about econometrics, guys. If you know the hardcore of what you're doing, the reading of the results is extremely simple. Okay, so what can you tell me about the R square? Come on, I have already mentioned this a couple of minutes ago. What is R square here? James?
77% of the variability of Y can be explained by the variability of X.
Beautiful. That's it. Got it? Now, someone can explain why the R square with the adjusted R square, they are different. They are significantly different.
This is a much smaller sample size.
Definitely. We have 10 observations only. Okay. So which one are you going to use? Which one do you prefer to use in this case?
Adjusted.
Adjusted. Okay. Now, the standard error, we're going to talk about the standard error later. What about is there a goodness of fit? Is a goodness of fit of the model or not? So goodness of fit, guys, is another way of telling to you, is linearity a good representation of the model, yes or no? Okay, you tell me. This Anova, guys, is called Anova F Test or goodness of fit test. Okay, you tell me, guys, how good is our model? The linear model fits the data or not? Guys?
Yes.
Yes, how do you know that?
Because the significance of F is less than the alpha.
Right, and what is the null hypothesis of the F?
That there is no linear relationship, so you reject.
Exactly. So the linear relationship holds here. Agree, everyone? What we see here, guys, we're going to see any other statistical package, so it's exactly the same. Okay, so what is the null hypothesis for the intercept? Null hypothesis. So now we're going to read row by row. What is the null hypothesis here, guys? Is the intercept significantly different from 0 or not? What is the null hypothesis, first of all? What are you testing?
Whether it's statistically significant.
It is statistically significant. This one here?
No, I'm saying that's what it's testing.
Oh, yes.
Whether or not it is,
Yes. So, but the null hypothesis, guys, is that it is not statistically significant, correct? Perhaps you pronounce this correct. So basically, alpha equals 0. This is my null hypothesis. Meaning that what our null hypothesis is that it is not statistically significant, right? So what can you tell me about that hypothesis, guys? Now use the p-value. At the 5%, always is 5% at this point.
Do not reject.
You fail to reject,
Yes.
right? Because 0.44 is not smaller than 0.05, then you fail to reject. So you can, you can argue that statistically this number here is equal to 0. Okay, perfect. Now, what about the second one, the x1? What is the null hypothesis for beta 1? This is what I call beta 1. This is what I call beta 2. What is your hypothesis for beta 1?
The null hypothesis is that beta 1 is equal to 0.
Correct. And you see the confidence intervals. Now I want you to use this one here. What is your conclusion?
I do not reject.
Yeah, fail to reject. Agree or not, guys? Yes. And why is that? Because the hypothesis number of 0 falls in between these two numbers. So you fail to reject. So indeed, this one also can be considered 0. And the last one, guys, what can you tell me about the last one using the p-value?
The p-value is less than alpha, so you reject that one.
Right. So this one here is statistically significant different from 0. Make sense?
Professor, just one quick question. How is this smaller? Isn't it equal?
Which one?
For the last one, x2, isn't it 0.022, and then the lower 95% is also 0.022?
Oh, well, you know what? This was a matter of luck. Not a matter of luck, but yes. No, not necessarily this is true. Huh? Not necessarily. Oh, you mean 0.022, this is 0.022, and this is 0.02. So 0 is not in this interval. You see that?
Oh, okay, got it.
Yeah, it's 20. Yeah, it's 20 here, and this is one is 0.02. So, and 0 is not in this interval, so thus you reject the null hypothesis also.
Got it. Yep.
Okay, perfect.
Sorry, Professor, can I just ask that you, the first step when you were inputting the data into Excel, can you just quickly run through that again?
Yeah, of course. So you go data, then you select data analysis, then you select in data analysis panel regression. And then in the regression, you simply start writing the input. You click here in this arrow here and select your Y. Then you select your X. So your X are these two guys. Then you need to be sure that you tell Excel, I have my label. So labels mean simply the name in the first row. The confidence level, you can change this confidence level. So for example, this one here, you see the third one, guys, the 0.092. If I decrease this to 90%, so my significance level is going to be 10%. What do you think is going to happen here? Are we going to fail to reject, or we're going to reject? What do you think?
Reject.
So if alpha, if alpha is 0.1, so 10%, this number here is going to be smaller than 0.10. So it implies that I will reject my null hypothesis, correct? So this one is significant at 10%. So, okay, so let's do the output range. Let me just write the output range somewhere here, just to compare. And then you click OK. Let me change the. Take a look. Nothing changes, huh? Nothing changes here.
Professor, I have a quick
Yes.
question. So
Yes.
should we be looking at multiple R because this is
No, that the multiple R, we are not going to talk about this until later, because the multiple R is not anymore the coefficient of correlation. Okay, it's a mixture of cross correlations. I will explain that later. Okay.
Okay.
Yeah, forget about the multiple correlation. We don't necessarily use this one here. We use these two numbers here. Okay.
Got it.
Now, guys, and this was always a question that I had in the past, and I talked with the people from Microsoft Excel. You see that there is two numbers, two blocks here, lower, upper, lower, upper. Do you see that? Okay, this only works if you have 95%, you're going to have these numbers repeated. Do you see that? Now, if you add a different percentile, a different significance level, what is going to happen is now you see the use. So now we have the 90% here and 95% here, so you can basically understand. So now take a look to this one here. If you use the confidence intervals, using the confidence intervals at a 10% significance level, do you fail to reject or do you reject the null hypothesis? Using confidence intervals, so use this one.
Reject.
Reject, exactly. Why? Because when you use confidence intervals, guys, you use, what is my hypothesis that alpha equals 0? Well, no, beta 1 equals 0. And then I ask, is 0 in this interval? No. Okay, so fail to reject. You can see, this is what you are going to learn, guys. In some papers, they tell you significant at 5%, significant at 10%. Okay? Correct? Questions? Okay, so we can move. You have, guys, in your package, guys, I've done this. Okay, you need to do that, but I describe every single one. Here is the formula. How do I get the numbers? Okay, so you have a lot of material here that you can read. This is more for understanding what we are doing. Okay, everything is well described. You just review this part here, and you're going to learn what is my null hypothesis, what I'm doing here. No, I have here the algebra. Remember, we have the x prime y. So my formula was x prime y to the minus 1 x prime y. Do you remember? Remember the formula that I wrote for you? So if you do all the steps here, guys, all the steps are described here, then you arrive exactly to our results. Take a look. The first element is going to be my a, 0 minus 0.216. Remember that? This is what we got here. Then you have your 0.085, then you have your 0.113. Right? It's just to show you guys how the algebra, linear algebra works in all its work. Works beautifully. Of course, it must work. Got it? Okay, questions?
Professor, for that page, I don't think you ever sent this page to us. For the two packets you sent us, the page that you just showed us on the one before was never in there.
Okay, so let me, are you sure? Okay, let me check that and I will be sure that you get it. It is really, just for understanding how this model works, it's good to know. Okay, guys, I will send you this then. Okay, questions? So we can move.
Will we need to be able to recreate this linear algebra?
No. What you need to do, you need to be able to do is this part here only. Only this part. Okay, for this model here. All this information here that you have is just for you to understand the model. Okay, it's what I've talked before. Remember, guys, I was not able to record the classes, so that's why I prepared this for you. For you, it's going to be less useful than for your colleagues, 2 years ago. Make sense? Okay, so now let's go. Let's continue moving. Now let's go into the model assumptions. So we are going to to start working with all the potential issues that we have with this model and how to solve them. What was the first assumption, guys? Do you remember? What was the first assumption? Guys, you need to study. And this was part of the Excel file, sorry, of the YouTube video that I prepared for you. Please, you need to take a look to that. The one that I developed all the model, the assumptions are there, are crucial, okay? So that this part is crucial, guys. The first assumption, yeah.
Linearity in the
Yes,
coefficient?
yes. So let's start with linearity. Linearity. Perfect. So what is the meaning of linearity, guys? So basically, that my model is simply alpha plus beta x plus my error. You agree? Okay. However, the linearity is linearity in parameters. Okay, so this is going to be crucial. We'll explain you in a minute. Guys, do you think that this model here can be solved using OLS? Let me see if I do. Let me see if I do. Yeah. Can I do something with this model?
You can log it.
Yes. So what I can do is I can what is called log linearize. Okay, and in economics, guys, the Cobb-Douglas function looks like that. Okay, so we always work with the Cobb-Douglas. We work with the log form of the model. Now, what is interesting about the log, guys, is that we have ln. If I take ln of everything, I will have ln of alpha xi beta. Remember that the ln of a product equals the sum, correct? And the ln of a number or a variable to powers of something is simply the product of the power times the ln of x. These are properties of these variables, of these operators. And so this is equal to ln of yi. So you can also use a OLS model for these models. Okay, so this is called the Loc model. And what is interesting, guys, is that beta represents elasticity. Okay, so the reading in economics, guys, elasticity is crucial. Do you agree? In marketing, everyone is talking about elasticity. I want to see how elastic is my product in order to increase the prices. Okay. Now, what I mean for that is linear in parameters. So what is that? What is the meaning of that? The meaning of that, guys, is that indeed you can have models like this one, and that the model still works perfectly. I can have yi equals alpha plus beta xi, beta 1, plus beta 2, the same variable squared as an error. Do you see? So what we have done here is not square the coefficients. What we are square is the variables. And that's perfectly feasible. So we can do that. So let me see if I can find, or at least I can create one example for you. Do you see Excel? Do you see my Excel? No. Okay. Forget about this formula. Do you see this data? Okay. Can you take 2 minutes, guys? Copy these numbers and do the regression. And tell me your conclusions very quickly. 3 minutes, okay? Well, I take some water. Ready? Everyone? Okay, 2 more minutes.
Quick question, Professor.
Yes, go ahead.
I'm not sure if I did it right in Excel, but I got quite a few negative numbers.
Okay, so let's take a look to that. So what is your R square?
0.7553.
0.755. Yeah, well, it looks very, very good R square, right?
Mhm.
Okay, so let's wait a couple of minutes and we do all together, okay?
Professor, I just had a question on just the functionality of Excel. Like, whenever I do the linear regressions, it puts the linear regression on a separate sheet. So I was just wondering how you keep the data.
Yes, yeah. I will show you in a minute. Yeah, that's a good point. Okay, guys, so what I will do and what I suggest you to do, remember when we started statistics, what was the first part of the statistics we studied? You remember? What was the first part?
Descriptive statistics?
Yeah, descriptive statistics, remember? And it has a reason, guys, because you don't jump to the pool without knowing that the pool has water, okay? And what I mean for that is that just be careful. It's better if you take a look to the data for a minute, analyze the data, check the data, do some graphs, etc. before going into the models, okay? That's important. Why? I will show you in a minute. What I will do here is I will simply represent my X and Y. Where's my insert? I will do my scatter. Okay, so I can start this, I imagine, at 40. So let's start. Let's start this at 40, so we can see this better. You see, this is my data, guys. So let's even 45. Do you see my data? Guys, you agree? This is what we have. Guys, do you see this one? Yep. Okay, perfect. So remember that there is a way, an easy way to do this in Excel in the graph. So what I will do is I will simply say, you know what? Okay. So I click in one of the dots. Sorry. Click in one of the dots and then right click, add trend line. If we add trend line, let's start with the linear. Let's display my equation and let's display my R square. So this is my regression. I assume that you get this one here. Rashad, really? 0.7553, more or less, right? This should be your regression, more or less. Do you agree? Okay, so now let's do this in not in the graph, but in I want this to appear in Excel. So let me move this somewhere. Okay, so what I do is I go data analysis, regression, and then I need to select what is my Y. Remember, my Y is this one here. Correct? So the order here is reverse. I don't know why I did it. And my X is going to be this one here. Agree with me? And then I have labels. I want to have a 95 confidence level. I want to put this here. And then in order to avoid creating a new tab, what you do is you take a look here, output range, Robert. Okay, output range, and then you click here, and then you select, I want this to appear in L1.
Great, thank you.
Got it? And then you have this one here, and then you press your results, and here are the results. I will just use 3 decimals. And this is what I get. Everyone is with me. So your linear relationship, your linear model works like that, and everything is significant. Are you with me, guys? Do you got these numbers? Okay, perfect.
Quick question,
So,
Professor. How do
yeah.
you shrink the decimals and make it
Oh,
3?
yeah, you go home. Then you go here in this part here, you have a dollar, percentage, etc. You just click in the lower part, and then you simply select number of decimal places, and use a comma if it's more than thousands, and then click OK. Okay, perfect. Okay, guys, so you have your result. If you haven't seen the graphs, okay, these are your results. You're going to be very happy. 75%, cool. You know, it's very good. It is. The linear representation is a good one. And these two are significant because the p-values are less than 0.05. So you're happy with your model, correct? Now, take a look at a careful look to your data, guys. What the model is trying to do is trying to fit the errors. Okay, it's trying to move to minimize the sum of the square of the errors. Do you agree? But then, if you do an inference, guys, okay, inference is a kind of a educated guess, educated forecasting. If you continue the line, if I tell you guys, okay, let me see here. If x equals, let's say 70, what is your expected y hat? What is your expected value of y? How do you do that?
Use the intercept and the
Yeah, so
beta
exactly.
value.
This is going to be this number times my beta times this number here, correct? So what I'm doing is simply, guys, remember what I've done. If x is 70, yes. So, oh, times, forget about that. Is M17 plus. Okay, now it makes sense. Do you agree?
Yes.
So it should be 48.264. So basically what I'm saying, guys, is that this number is going to be around this part here. Agree with me? Please pay attention and then you copy, guys. But you agree with me? If it's more or less 70, according to my model, the resulting y is going to be in this part here. Agree? Guys, agree with me? However, guys, take a look to the data. The data appears that is going not up, is leveraging, and perhaps it's going to go down. Perhaps it's leveraging and going down. Do you see? So by inspecting your data and your model, guys, you can say, I really there's something that I don't like a lot about this model. Correct? And then you are going to remember, oh well, Professor Rengifo told me that I can do a model that is linear still in the coefficients, but is not linear in the variables. And perhaps this is going to help what I'm doing. Got it? Now, I will show you first in the graph. If you do click again, right click, add trend line. Then here, what you select is polynomial. Okay, and you can be playing with this, but let's assume order 2, because I believe it's order 2 already. And then what we do is, okay, display equation, display R squared, and I will move this somewhere here. Take a look, guys. Do you see the feed? Much better. Now, how I have created this variable, how I have created this regression. Okay, so that's the point. Do you understand what I'm doing? Now, what I will do is I will show you how this works. And we're going to be using this all the time. So this is the only time I will do this for you. And you're going to get it. So I will move y to be first. And then my model, guys, is y equals alpha plus beta x plus beta 1x, beta 2x squared, correct? So I need to create my variable x squared. And what is x squared? Is x squared. So I'm simply squaring every single number. Okay? And now you were in a univariate model. Now you have a bivariate model, multivariate model. And then you simply run again your Euler's model. Correct? Okay, do this, guys. And be sure that you get the exact numbers as, let me. And be sure that you get these exact numbers here. 92% R squared, etc. Can you do that? So basically what I've done, I created y, x, this is data. And what I have created is x squared. So you're not violating the linearity assumption of the model, guys. Okay, you're not violating the linearity assumption of the model.
A quick question, Professor. When you go to do x squared,
Yes.
is there a faster way of doing it instead of doing it one by one? Like just setting the formula for it to apply across?
Oh, no, no, you do only the formula for the first one. Okay, this is let me show you. You write this formula equals this one here square. Okay, once you have this formula, so let me delete this part here. Then what you do is you see that appears across here in the lower right corner. You see, yes, appears not a white cross, a black cross. So you see that. Once you have that, double click. You see that?
Oh, gotcha. Thank you.
Perfect. Yeah, that's beautiful. This one is perfect. Okay, now you have this. Okay, please run the regression in a couple of minutes. And just be sure that you have, of course, guys, you can see the fit is much better. Okay, there is a lot of advantages of the square of the linear regression, but on the square of the variable. Ready? So I will do this very quickly. Again, it's the same procedure. Okay. Data analysis, regression. I just need to change my y and x, x's in this case. My y is this one here. My x is w and x, the positions. Now I want my output range to be located in C1. And that's all. Okay, I will simply adjust. And that's all. Do you see that, guys? If you compare these numbers, minus 425 with this here, etc., you can be sure that they are exactly the same. Make sense to you? So, guys, if you see that the data has some curves, you know, perhaps it's a cubic, so it goes, it doesn't do simply the hump, so it does like that and then like that. You know, the typical cost function in economics, guys, that can be a cubic function. Okay, and Excel provides you, and we are going to see that in EViews also is much beautiful and easier. But you can start adding a different function. So, for example, if you click here, you want to still do a polynomial, but you believe that this is a cubic. So you simply go here, cubic, and take a look to what's going on. Let me change the color. So let's put the cubic as a red one. You see that? Perhaps the cubic is much better, guys. Let's take a look to the. Where's my options here? Okay, so I will put the cubic here. Take a look, guys. And the cubic is better capturing the last piece of the equation. Do you see that? If you think about returns here, apparently this was growing faster. You know, it stabilizes, but perhaps it's going up again. Versus the quadratic that tells you that it's going to go down. Perhaps it's much better the cubic here. How do you run the cubic if you want to run the cubic? I will not do this, but how you create your data for the cubic? What do you need to do? Okay, we'll copy all this one here. What do you need to do? Well, I need to create another variable, guys, that is simply x cubed. And x cubed is x cubed. Oh, sorry, is this one to the power 3? And then I copy, and then you do the regression. If you do the regression, what you should get is these values here. Guys, makes sense to everyone? Yep. Okay, so indeed, the OLS model, guys, is very flexible. Okay, so just don't be afraid of linearity. You can linearize the model using logs, or you need to analyze the data. Perhaps you don't need to do anything. It's simply that you need to use different powers of the data to capture better the relationship. Got it? We're going to do a lot about that later, but makes sense to you? Do you understand? Okay, so linearity doesn't mean that you're not able to curve the function. You can curve the function. The only thing you need to be careful is that you don't have beta square, or you don't have beta to the power 0.5. You cannot have that. The betas are going to be always linear. Okay, so power 1. Make sense to everyone? Let me say this. Okay. So let me go back to my screen. No questions, guys? Okay, so linearity is good. Perfect. So we have done the linearity problem. So remember, you can do this stuff. This one here is okay. This one here is okay. And of course, this one here is okay. Now, what is the second assumption, guys? A very crucial assumption.
The sum of the expected error is the sum of the expected value of errors of the sum of, or the expected sum of errors is going to be 0.
Yes, the expected value, yes, the expected value of errors, okay?
Yeah.
Is going to be equal to 0. Okay, so basically up and down, they're going to cancel out. Make sense? Okay, so now, guys, what is interesting is, please take a look to the video. This by construction is satisfied. Because remember, guys, what we're trying to do is we're trying to find the A and B, alpha and beta, that satisfy the sum of the square of the errors equals 0. Okay? By construction, this one is satisfied. However, careful deleting, with not deleting, I will say deleting the y-intercept A. So what I mean is that if check first if A is statistically significant before removing this one, before removing. Otherwise, guys, what is going to happen is all other coefficients are going to be, this is the worst nightmare, guys. Oops, biased. This is economics' worst nightmare, having biased results. And I will show you in a minute. Let me find an example.
So the results are biased if A is statistically significant,
No. Imagine.
or if
You
just,
know that
or
A
if you just
is,
don't.
yes, A is statistically significant, okay? But you decide to delete A. You know, I don't know why, but the people sometimes say, oh, you know what, I believe that A is 0. Okay, remove A 0, because I know that by theory, A is 0. Got it? So you remove it. But you haven't checked if A indeed is statistically equal to 0. Got it? If you do that, guys, everything is going to be wrong. And I will show you in a minute. If you just give me 1 second, I will find something. Interesting. Where can I find this one? Yeah, this one here. Can I help? Oh, you don't see Excel, sorry. Share this. Okay, guys, so let me, so this is another example. I will give you all this stuff, okay, because I just prepared this stuff. So take a look to what happens. Let me move this from, just to show you better. I want this to be from 1 to 3. And this to be 9 to, oh, no. Yeah. And the other one just to be from 9. You see? Okay, so which one is with I don't know which one is which. In any case, let me see this one here. Let me delete this one. Delete. Okay, so you know how to do this stuff, but I have a series of points here. Make sense? Okay, and then what I will do is I will simply run my regression, add my trend line, linear, and I want to simplify these two. So this is my common OLS model. Got it? Now, imagine, guys, that I decide that the intercept for some reason should be equal to 0. Okay, what I will do is the following. So I will do add trend line, the same, but here what I will do is I will set my intercept to 0. And what you need to understand is the following. Take a look. And this is the misleading. So this one here is the one that is equal to 0. So let me put this in red. Perhaps I can change this. So the red one is the one that you assume that is equal to 0. Got it? Now, guys, take a look to the following regression. If you just take a look to that, are you with me, guys? Guys, are you with me?
Yes.
Yes. Okay, take a look to what happens. If you just trust in the R squared, which one is better? So remember, this is with intercept equal to 0, and this is with intercept equal to whatever.
Zero intercept.
Yeah, 0 intercept. The second thing that you need to realize, if I force the intercept to be 0, compare the coefficients of x, 8.134 versus 7.13. So the results are going to, if you do forecasting with this stuff, if you do inferences with this one here, the results are completely different. Agree? However, guys, take a look. Do you remember our assumption? This one here is my observations. This one here is the results of the model. These ones here are my errors. Do you agree? Okay, so my errors are simply my observations minus my fit. Observation minus fit, you have your errors. Sum of errors equals 0 by model construction. Do you agree? So that's the idea. The expected value of the errors is equal to 0. So if you use the model, you can see that the errors, guys, at the end of the day give you 0. Satisfied, 100%. However, guys, if you force the model to have an intercept equal to 0, what is going to happen? This is with an intercept equal to 0. Take a look to the errors. Okay, these are my errors. What do you think? The sum of the errors, or the expected value of the errors, is not 0. And this one here, guys, is terrible. Okay, it is really terrible because everything is going to be wrong. Not only in terms of bias, but in terms of efficiency, in terms of everything that you can imagine is wrong. Make sense to you? Okay, let me do some math in a minute, but do you understand? So the only way in which you can eliminate the alpha is when you have a statistically non-significance. Okay, in that case, yes. In that case, if you have a statistically non-significant, okay, remove A is not a big deal because the coefficients that the model is going to be satisfied. One of the main assumptions of the model is going to be satisfied. Got it? Now, let me.
Excuse me, Professor. I just want to make sure I understand the point you're making. So if you try to eliminate the alpha, then basically the sum expected value of errors is no longer 0. So the methodology doesn't hold?
Exactly.
Okay, thank you.
Exactly. Yeah, and all your results, all the coefficients that we have found here, these numbers here, are completely are biased. So this means that your results are terrible.
Okay.
Perfect. Okay, so now let me go back to my writing. Let me talk a little about so what is unbiased? Okay. Guys, I will do some math here, matrix algebra. Please, if you don't understand, at least try to get the idea, okay? So we know that B equals X transpose X to the minus 1, X transpose Y. Do you agree? And we know also that Y, we have done this at the very beginning, is X beta plus an error. Okay, so let's call this 1. And let's call this 2. And what I will do is I will do 2 in 1. So B equals X prime X to the minus 1. X prime, I'm replacing Y for all this one here. Then I simply multiply and I obtain X prime X to the minus 1. It's the same as normal algebra. First I multiply by this element, X times beta, plus X prime X to the minus 1, X prime epsilon. Got it? Now there is a property, guys, I will mention this here. A times A to the minus 1 equals 1, identity. Right? So this part here basically is going to be equal to 1. And I will take the expected value before doing that. It's going to be this part equals 1, identity, times beta. So beta is the only one that stays here, plus X prime X to the minus 1. This is a number. It's this comes from data. And then I have here expected value of X prime E. Okay. So do you remember, guys, there was one of the assumptions in the model, and I show you this when I do the mathematics for the univariate model. This one here is what we call covariance of XE. And we say that this must be equal to 0, right? This condition here is called orthogonality. Let's see, orthogonality. Now, if we have orthogonality, take a look to what happens. Expected value of my coefficient beta is going to be equal to my population beta. So this is what is called unbiasedness. Okay, so in average, guys, your beta estimate is going to be equal to your population slope, or to population variables, we'll say. Okay, if we don't have results are not unbiased, guys, our results are going to have all this second element here. That can be whatever. Do you agree? Guys, do you agree? If this condition does not hold, take a look. Do you see that? If the covariance of XE does not hold, all this part here is going to be biased. Do you agree with me or not, guys? So basically what it means is the following. So this is what you want. So you want in expectation your beta to be a good, that is based on sample, your B that is based on a sample, equal to the population beta. That's what you want. This is unbiased. And this unbiasedness comes from this part here, that the covariance of X and E, okay, is equal to 0. So they don't, the errors are not related with the X variables. If this condition holds, we have unbiasedness. If this condition does not hold, we are in troubles, okay? Because our result is going to be biased. And if our result is biased, guys, it is really crap. It is whatever, except a good result, okay? Now, can you pay attention for a minute to this one here? Covariance of XE. The covariance of XE is simply, and this is the only hard math that I will write from now. And then well, it's not hard. It implies you need to know some statistics here, but in any case, this is X minus X bar that multiplies E minus E bar. What is E bar? These are the means. Okay. Take a look to what happens here. So if I multiply this one here, this is the expected value of, I multiply this by this, XE minus XE bar minus X bar E minus X bar E bar. Do you agree, guys? Now, what is E bar? E bar equals the expected value of E. What is the assumption of this one here?
That it's 0.
It's not assumption, it's model, yes, model assumption also is equal to 0. So if this is 0, guys, you can see that this part disappears and this part disappears, correct? And also then now I can apply this one here. This is going to be equal to E of XE minus X bar is a constant, expected value of E. So what is that? This part disappears, right? Because this is 0. This part disappears. So at the end of the day, guys, the covariance of XE is simply the expected value of XE. This is exactly what we got in here, the covariant expected value of XE. Got it? Now, take a look to what is the problem with this stuff. If this one here, that is equal to the expected value of E, is not 0, so what is going to happen? This number here, this covariance is not going to be equal to this one here. It's going to be a much larger number. It's going to have all other components. Do you agree? Correct? So this implies, guys, that this number here is not going to be orthogonal anymore. And if we don't have orthogonality, we have not unbiasedness. Then we have the issues. Make sense? So that's why what I'm telling to you is that when the only way that you are going to satisfy this one here is very simple. Don't delete the alpha. If you delete alpha, it must be with a reason. And the only reason that allows you to delete alpha is because you have observed that it is not linearly, sorry, it is statistically not significant. Got it? Make sense?
Professor, can you go back to the Euler page very quickly?
Yeah, of course. I will go there. Okay.
Then you just said the only reason that you would delete the alpha is because you've observed that alpha is not statistically significant.
Completely right. Yes. Yes. I don't know, guys. I have seen a lot of research, and it's basically of students, not of course people that is doing this a lot. But I don't know why they say, you know what, the alpha is 0 for any crazy reason. Sometimes the reason is logic. Okay. For example, if you don't advertise, perhaps your sales are going to be 0. Of course, it's not true, because sometimes you have what is called baseline sales that you don't need to advertise and you want to sell. Got it? But sometimes you can argue that if there is no advertise, the sales should be equal to 0. Got it? So basically, you are going to force your regression. Okay. And sometimes the people do this for a reason. Sometimes they know that, imagine if your slope is like that, okay? And you are the, so let me present you an example of why the people can do that. So imagine this is marketing expenses. And imagine this equals sales, right? And imagine that my cloud is like that. Are you with me, guys? So if I do my OLS model, my data is going to be like that. My fit line is going to be like that, correct? Then, of course, my y-intercept is going to be this one here. So this one here is my A. Do you agree? So now, for a marketing guy, what is do you like to have a flat line, or do you want to have a more steep line? Which one is better for you?
Steeper.
Steeper. Why? Because remember, guys, that here the model is going to be sales equals alpha plus beta marketing. Do you agree? Plus my error. So this beta measures what? The impact of marketing on sales. Do you agree? So if you're a marketing guy, what do you want? Well, you want beta to be larger, correct? Yeah, because then I can argue, you know what, put more money in marketing because the impact is very strong. So the one way of doing that is what? How do I force this line to be steeper? How do I do that? Guys, I disappear A. So disappear A implies what? That my model, I will call sales blue, disappear is simply equal to beta M plus E. Correct? So this implies the following. What you're doing is you're forcing your model. So let me, okay, up to this, and here I will have the line. This is going to be my line. My intercept is 0, and my slope is going to be what? Beta blue is going to be larger than beta red. Make sense? Now, what happens with this beta, guys? Another words, more technical words. Biased. Scrap. Really, you cannot use that number. Okay, you cannot use the numbers because your forecasts are going to be completely out of focus. Do you see that here, guys? If you increase your expenditures on marketing, your forecasts are going to be around here. They are completely different to what you have been observing in real life. Make sense? Okay. Okay, guys, I think we stop here. So we have, please, next week we start with eViews. So everyone should be with eViews. I will send you a data set to test, and we're going to start working with eViews, and then we're going to do more interesting stuff. We can start running now. Guys, please study, okay? Study, because you're going to get lost, and you're going to get lost on the fundamentals of econometrics. And these are the fundamentals of econometrics. After that, the models are more repetitive. You're going to say, oh yeah, I get this idea. I know the p-value. I know what is alpha. I know what is beta. I understand all these concepts. I know it's correlation, R squared, F, X squared. I know that already. So this part here is the crucial for understanding other models in the next future. Make sense? Okay, so study, guys. And we see you
Professor, can I have a word with you after class?
Yes, of course. We need to do this very quickly because I have the Euler class coming up.
Yeah, sure.
Okay, guys. See you soon. Have a nice week.
Thanks.
Take care.
Thank you,
Thank you.
Professor.
Hi, Professor.
My pleasure, guys. Take care.